Students, in this video, we will discuss about the application of Schrodinger wave equation to the particle which is trapped in a one-dimensional box. Remember, in the last class, we derived the Schrodinger wave equation for a particle, and also we attempted to understand the physical meaning of wave function psi and square of the wave function psi square. When a Schrodinger wave equation is applied for a particular system, okay, and the Schrodinger wave equation is solved, we get two important information about the system. One is the energy of the particle or particles present in the system. The second is the wave function. Okay, so here also we apply the Schrodinger wave equation to a particle that is trapped in a one-dimensional box. We apply it and solve the Schrodinger wave equation. We get an expression for energy of the particle as well as the wave function of the particle. We do not have a similar problem or system in chemistry such as a particle in a one-dimensional box. We do not have such example, but this particle in a one-dimensional box, though it does not have any direct physical relation to any of the chemistry problem or chemistry system, it can be roughly applied to the pi electrons moving in a conjugated molecules. We all know that the pi electrons in a conjugated molecule are delocalized. Okay, it means they can move throughout the conjugation. So the particle in a one-dimensional box can be roughly assumed to be equivalent to the pi electrons traveling in a conjugated molecule. So it is only a rough application. Okay, but what is the advantage of studying such type of system is, once we obtain the expression for energy and wave function, we will analyze those expressions and try to interpret some of the important informations we obtain from those equations. I repeat, even though we do not have any system in chemistry to which this particle in a one-dimensional box fits into, but still this is a very important topic in chemistry, because the final results we get, that is the expression for energy and expression for the wave function, it gives some important information about the quantum mechanical results. So in that aspect, this is very important. So first let us define what do you mean by a particle trapped in a one-dimensional box. So you have a particle of mass m traveling along x-axis. Okay, so this is the x-axis. Let us take it as origin. Okay, x is equal to 0. So a particle of mass m is allowed to travel only in one direction, that is along x-axis. Okay, and we are assuming that this particle can move only between x is equal to 0 and some point x is equal to a. The particle is free to move anywhere between x is equal to 0 and x is equal to a. The particle cannot move beyond x is equal to a or beyond x is equal to 0, but it is free to move anywhere between x is equal to 0 and x is equal to a. So how to restrict this particle within this region? ಈ ಪಾರ್ಟಿಕಲ್ x is equal to a ಇಂದ ಅಥವಾ x is equal to z ಇಂದ ಹೊರಗೆ 0 ಇಂದ ಹೊರಗೆ ಹೋಗದಿದ್ದಾಗೆ ಯಾವ ತರ ರಿಸ್ಟ್ರಿಕ್ಟ್ ಮಾಡಬಹುದು? We can restrict it if we assume that outside x is equal to a, the potential energy V is equal to infinity. So by setting potential energy is equal to infinity outside this region, we are restricting the particle to move only between x is equal to 0 and x is equal to a. So if the particle wants to cross this point x is equal to a, it must acquire infinite amount of potential energy. And since it is impossible to attain infinite amount of potential energy, it is difficult for the particle, that is, it is impossible for the particle to cross this barrier x is equal to a or x is equal to 0. So there is some type of wall. Okay, there is some type of wall at x is equal to 0 and x is equal to a, and the height of this wall is infinite. Height of this wall is infinite. So if the particle wants to escape from this region, it has to climb this wall of infinite height. That is, it should have infinite potential energy, which is not possible. So the particle is trapped within this region. So that is why this system is called as particle trapped in a one-dimensional box. And this particle is a free particle. What do you mean by a free particle? It means that the particle is experiencing no force. There is no force acting on the particle. Remember, in physics we have studied that if no force act on a particle, then its potential energy should remain constant. And for making our mathematics easy, we are assuming that the potential energy of the particle inside the box is equal to 0. I repeat, this particle is a free particle. It means no force is acting on the particle, and when there is no force acting on the particle, its potential energy remains constant, and we are considering that constant as equal to 0. So we are assuming that potential energy is equal to 0. It need not be equal to 0. It should only be a constant. It might have been 5 joules or it may have been 10 joules, but we are assuming that it is equal to 0, just to make our mathematical derivation simple. So this is the definition of the particle in a one-dimensional box. Now let us apply the general Schrodinger wave equation to this particular problem and try to find out what is the energy and what is the wave function of the particle. So to begin with, we will use the general Schrodinger wave equation, okay, a time independent Schrodinger wave equation. So since this is a one-dimensional problem, because the particle is traveling only in one dimension, we have to use the one-dimensional Schrodinger wave equation. So let us begin with the general one-dimensional time independent Schrodinger wave equation. Okay, we have to begin with the general one-dimensional time independent Schrodinger wave equation. It is d square psi of x divided by dx square plus 8 pi square m divided by h square into e minus d into psi of x is equal to 0. So this is the general equation which is applicable to any one-dimensional system. Okay, this is applicable to any particle of mass m moving along x-axis. Now let us apply this general equation to this particle in a one-dimensional box. What is the important characteristics of particle in a one-dimensional box? The important characteristics of the particle: potential energy V is equal to 0. I repeat, the characteristic of the particle trapped in a one-dimensional box is V is equal to, potential energy V is equal to 0. So for a one-dimensional box, potential energy V is equal to 0. So if I substitute this condition in equation 1, therefore the Schrodinger wave equation for the particle in the one-dimensional box is d square psi of x divided by dx square plus 8 pi square m e minus v, but v is 0, so 8 pi square m e divided by h square into psi of x is equal to 0. So equation 1 is a general equation which is applicable for any one-dimensional system, whereas equation 2 is the Schrodinger wave equation applicable only for a particle in a one-dimensional box. Why it is applicable for the particle in a one-dimensional box? Because we have substituted the condition V is equal to 0, which is applicable for this particular system. So equation 2 is the Schrodinger wave equation for the particle trapped in the one-dimensional box. It is a differential equation, and if we solve this differential equation, we can obtain an expression for energy of the particle and the wave function of the particle. So before solving this equation, what we will now do is, if you look at this term 8 pi square m into e divided by h square, this term is a constant, because 8 pi square and h square is a constant. For a given particle, mass is a constant and energy is also constant. So this entire thing can be treated as a constant. So let us write equation 2 as d square psi of x divided by dx square plus alpha square into psi of x is equal to 0, where what is alpha square? Alpha square is nothing but 8 pi square m into e divided by h square, which is a constant. Okay, so alpha square is nothing but a constant. So now we have to solve this differential equation 3. Okay, this differential equation is a well-known form of differential equation. You have studied this type of differential equation in your basic physics and mathematics course. Okay, maybe in PUC you have studied this type of differential equation, and when we solve this type of differential equation, the solution is either a sine function or a cos function. So in most of the case, what we do is we take a linear combination of sine as well as cos function. Okay, remember, sine function is also a solution to equation 3. Cos function is also a solution. So we select the best possible solution, which is a combination of sine as well as cos. Okay, so the solution, the general solution to equation 3 is psi of x. So if I solve equation 3, differential equation 3, we should get an expression for wave function psi of x, and the general way of writing the solution is a into sine alpha x. Where does this alpha comes from? From here. Here I have alpha square, that has become alpha, plus b into cos alpha x. So this is a general solution for equation 3. Whether this is a solution or not, you can find it yourself. If I substitute equation 5 in equation 3, okay, you can easily prove that equation 5 is a solution to equation 3. That we will not do here. Okay, so here a and b are some constants whose value we have to find out now. Okay, a and b are constant whose value we have to find out. So how to find out the values of these constants? These constants are obtained when we solve this differential equation. Now how to find out the values of these constants a and b? Remember, whatever steps I am discussing here is very important, because the similar procedure will be applied for other systems also. So that is why this application is very important. Though this does not have direct physical importance in our chemistry problem, still it is considered as important, because the mathematical procedure that we are establishing here will be used for when we apply Schrodinger wave equation to other realistic problems such as hydrogen atom or simple harmonic oscillator, so on. So please try to understand the mathematical procedure. This will require again and again. So how to find out the values of these constants? Remember, the values of these constants a and b can be obtained by applying a condition called as boundary condition. So what do you mean by a boundary condition? It is nothing but the condition applied at the boundaries. For example, in this particular system, you have two boundaries. One is x is equal to 0, the other is x is equal to a. So what are the boundary conditions, or what are the conditions at x is equal to 0 and x is equal to a? So if I apply those boundary conditions into equation 5, we can find out the values of a and b. So the values of a and b values are obtained by using the boundary conditions. So they are obtained by using boundary conditions. So now let us understand what is the meaning of boundary condition. as I already told you, okay, this particle is restricted to move only between x is equal to 0 and x is equal to a. So this particle can be anywhere between x is equal to 0 and x is equal to a, but it cannot cross these boundaries. You cannot find this particle lying here, or you cannot find this particle lying here. So what is the probability of finding the particle outside this box? The probability of finding the particle outside the box should be equal to 0. And how do we calculate probability in quantum mechanics? If psi is the wave function, the probability is given by psi square. So here psi square of x, psi square of x okay, so psi square of x represents the probability of finding the particle at position x. So for all values of x greater than a, that is outside the box from the right side, psi square of x should be equal to 0. Similarly, for all values of x less than 0, that is the left side of the box, okay, outside the box again, the probability of finding the particle should be 0. So psi square of x will be equal to 0. So if psi square is 0, then psi should also be equal to 0, because square of 0 is also 0. So this implies psi of x is also equal to 0. This also implies psi of x is equal to 0. So I am rewriting this, for x greater than a, the value of wave function becomes 0. Similarly, for all values of x less than 0, the wave function value is 0. Now we are using a condition that since psi of x is a well behaved function, okay, I already told you we only use well behaved function in quantum mechanics. What do you mean by a well behaved function? It should be finite, single valued, continuous and normalized. So since psi of x is a well behaved function, that is, it must be a continuous function. It must be a continuous function. What is the meaning of continuous function? That it should be a smooth function. The value of psi of x should change gradually or slowly with the change in the value of x. So by using the condition or the definition of continuous function, okay, it can be shown that if psi of x is 0 for x greater than a, it implies that psi of x is equal to 0 at x is equal to a. Why? Because if I take a point that is very close to x is equal to a, but just outside, okay, illೊಂದು point imagine ಮಾಡ್ತೇನೆ which is very close to x is equal to a, just outside the box, okay, here the probability of finding the particle is is 0. So it means psi of x is 0 at this point. But since this point is very close to x is equal to a, because psi of x should be continuous, we are assuming that even at x is equal to a, the value of psi of x is equal to 0. ಯಾಕಂದ್ರೆ ಈ point outside the box, okay, ಇಲ್ಲಿ psi of x is 0. So at this point is very close to this point. ನಾನು ಆಲ್ರೆಡಿ ಹೇಳಿದ್ದೇನೆ continuous function ಅಂದ್ರೇನು, it is a smooth function. The value of the function does not change in a very rapid way or in a very fast way as to change the value of x. So because of that, the value of psi of x will be 0 even at x is equal to a. ಅದೇ ರೀತಿ I can apply this similar argument here also. Suppose if I imagine one point outside the box but very close to x is equal to 0. So at this point the probability of finding the particle is 0. It means wave function psi of x is 0. But since this point is very close to x is equal to 0, because of the continuous property of the function, we are assuming that the value of the wave function is even 0 at x is equal to 0. So the second condition is, if psi of x is equal to 0 for x less than 0, because the function is continuous, we can write the psi of x is even 0 at x is equal to 0. So these two conditions are the boundary conditions for particle in a one-dimensional box. Okay, these two conditions are called as boundary conditions for particle in a one-dimensional box. So why they are called as boundary conditions? Because they define the values of the wave function at the boundaries, that x is equal to 0 and x is equal to a. Now let us apply these boundary conditions on equation 5 and try to find out the values of a and b. Okay. So I will rewrite equation 5 here again. The solution, psi of x is equal to a sine alpha x plus b cos alpha x. This is the solution to the Schrodinger equation 2. Now let us apply the first boundary condition. Let us apply the first boundary condition. Let us apply the first boundary condition. What is the first boundary condition? At x is equal to 0, psi of x is equal to 0. The first boundary condition is at x is equal to 0, psi of x is equal to 0. Let us apply here. Therefore, psi of x, that is 0, x value is, okay, psi of x is now 0 is equal to a into sine alpha into x, x is 0, plus b into cos alpha into x, but x is 0. So psi of x, which is 0 now, so 0 is equal to a into sine alpha 0 plus b into cos alpha 0. So I have substituted x is equal to 0 and psi of x is equal to 0. Okay, condition in equation 5. So this is nothing but 0 is equal to, this is sine 0, which is 0, plus b into cos 0 is 1. So this shows that the value of constant b is equal to 0. The value of constant b is equal to 0. So this equation 5 can be rewritten. Equation 5 can be rewritten as psi of x is equal to a into sine alpha x. So we do not require the cos term in our solution, because by applying the boundary condition, the first boundary condition, we have found out that b is equal to 0. So the solution to equation, the Schrodinger wave equation for particle in a one-dimensional box is not equation 5. It is given by equation 6, which do not contain the cos term. Okay. So we will use now equation 6 and not equation 5. So now we will apply the second boundary condition directly on equation 6, because this is the more appropriate solution. So let us now apply the second boundary condition. Okay, so let us apply the second boundary condition. What is the second boundary condition? The second boundary condition is, when x is equal to a, psi of x becomes 0. Okay, let us substitute here. Psi of x becomes 0 now, is equal to 0 is equal to a into sine alpha into x. X value is now a. Okay, I will write it inside the bracket to avoid confusion. So 0 is equal to a into sine alpha a, which means either a should be equal to 0 or sin alpha A should be equal to 0, or both may be equal to 0. So either A should be equal to 0 or sin alpha A is equal to 0. Okay, then only the product becomes 0. Now, which is true, mathematically both are correct, but in terms of physical reality, which is correct or which is more appropriate? What happens if A is equal to 0? Okay, if A is equal to 0, already constant B is 0, and now if I say A is equal to 0, then what happens to psi of x? Psi of x becomes 0 because A is equal to 0. So irrespective of the value of x, okay, psi of x is always equal to 0. So when I vary the value of x from 0 to A, whatever may be the value of x, psi of x inside the box is 0 for all values of x. What does it mean? If psi of x is 0, then psi square of x is also equal to 0. ಅಂದ್ರೆ ಅರ್ಥ ಏನು? psi square ಅಂದ್ರೆ ಅರ್ಥ ಏನು? Probability. So probability of finding the particle inside the box is equal to 0. I repeat, if A is equal to 0, psi of x becomes 0 for all values of x. If psi of x becomes 0, then psi square of x also becomes 0. And the probability of finding the particle at any point inside the box is 0. ಅಂದ್ರೆ ಅರ್ಥ ಏನು? There is no particle at all inside the box. A particle ಇಲ್ಲ ಅಂತ ಅರ್ಥ ಆಗ್ತದೆ. Okay, which is not true because we have assumed that there is a particle of mass m inside the box. So this argument shows that A cannot be equal to 0. So the only possibility is sin of alpha A should be equal to 0. Okay, so A cannot be 0. So sin of alpha A should be equal to 0. So therefore sin of alpha into A should be equal to 0. And when does sin theta become 0? Sin theta becomes 0 when theta is 0 or theta is 180 degree, that is pi, or theta is 360 degree, that is 2 into pi, or 270 degree, theta is 360 degree, 2 into pi, and so on. So in general theta should be equal to n into pi. So this becomes true if and only if the value of alpha into A is equal to n into pi. So if the value of alpha into A is n into pi, then sin of alpha A will be equal to 0, where n is 0, 1, 2, 3 and so on. Okay, but we again prove that the value of n cannot be equal to 0. The value of n cannot be equal to 0. Why? Because if n is equal to 0, right hand side becomes 0, it means alpha into A should be 0. If alpha into A is 0, either alpha should be 0 or A should be 0. Mathematically either alpha should be 0 or A should be 0, but A is equal to 0 is not possible. Why? Because A represents the length of the box. Okay, if I take this again, this is the one dimensional box, x is equal to 0, x is equal to A, the particle is inside the box. So the length of this region, this is x is equal to 0, that is origin, this is the other limit, x is equal to A. So this length is nothing but A, that is the length of the box, that cannot be 0. So A is equal to 0 is not possible. So this only possibility is alpha should be equal to 0. The only possibility is alpha should be equal to 0. But if alpha is 0 for all values of x, okay, so this is the symbol for all values, okay, of x. If alpha is 0, if I go back to equation 6, alpha is equal to 0 and substitute madidre, this entire term becomes 0. So again psi of x becomes 0 for all the values of x. It can become 0 for some values of x, but it cannot become 0 for all values of x. ಯಾಕಂದ್ರೆ ಅದರ ಅರ್ಥ ಏನಾಗುತ್ತೆ, if psi is 0 for all values of x, then psi square is also 0. What does it mean? The probability of finding the particle inside the box, the total probability is equal to 0, which is not possible because the particle is present inside the box. So this is not true. This is not physically acceptable. So alpha is equal to 0 is not acceptable. Okay, ಈ alpha is equal to 0 ಎಲ್ಲಿಂದ ಬಂದಿರೋದು? n is equal to 0 ಅಂತ ಸಬ್ಸ್ಟಿಟ್ಯೂಟ್ ಮಾಡಿರೋದ್ರಿಂದ. So n is equal to 0 is not physically acceptable. Mathematically it may be acceptable, but physically it is not acceptable. So n cannot be equal to 0. So therefore alpha into a is equal to n pi, but the value of n is 1, 2, 3, etc. So the value of n is restricted to take only integral values, but starting from n is equal to 1, 2, 3, etc. n cannot be equal to 0. See here how the value of n is automatically restricted to take only integral values. ಯಾಕೆ ಈ ರಿಸ್ಟ್ರಿಕ್ಷನ್ ಬಂದಿದೆ ಅಂದರೆ ಬಿಕಾಸ್ ಆಫ್ ದಿ ಬೌಂಡ್ರಿ ಕಂಡೀಷನ್ ಅಪ್ಲೈ ಮಾಡ್ತಿರೋದ್ರಿಂದ ಈ ವ್ಯಾಲ್ಯೂಸ್ ಆಫ್ n ಏನಾಗಿದೆ, ಇಟ್ ಈಸ್ ಓನ್ಲಿ ರಿಸ್ಟ್ರಿಕ್ಟೆಡ್ ಟು ಇಂಟಿಗ್ರಲ್ ವ್ಯಾಲ್ಯೂಸ್. ಅದರ ಕಾನ್ಸಿಕ್ವೆನ್ಸ್ ಏನಿದೆ ಅದನ್ನು ಆಮೇಲೆ ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಳುವ. ಓಕೆ, I will rearrange this equation. Therefore alpha is equal to n into pi divided by a. Let me take it as equation 7. Alpha is equal to n pi by a. Remember, in my earlier slide I had already written down an expression for alpha square. Okay, what is alpha square? Alpha square is 8 pi square m into e divided by h square. This is nothing but equation 5. And in equation 7 you have another expression for alpha. So what I will do is I will substitute equation 7 into the LHS of equation 5. Let us see what will happen. Okay, so substituting equation 7 into equation 5, alpha square ಬದಲು n pi divided by a, this is alpha square, is equal to 8 pi square m into e divided by h square. That is, this is n square pi square divided by a square is equal to n square pi square divided by a square is equal to 8 pi square m into e divided by h square. So pi square gets cancelled, and if I rearrange this equation we get an expression for energy of the particle trapped in the one-dimensional box. So if I rearrange this equation we get E is equal to n square h square divided by 8 m a square. Okay, and I am using a subscript n to indicate that the energy of the particle depends on the value of the integer n. Remember, n can take only integral values starting from n is equal to 1. So this is the expression, very important expression for the energy of the particle trapped in a one-dimensional box of length a. M represents the mass of the particle. N is called as a quantum number. Okay, what is quantum number we will discuss later. You have already studied what is quantum number in your PU classes. So n represents a quantum number which is restricted to take integral values, and h is Planck's constant. So this is the expression for the energy of the particle trapped in the one-dimensional box. Okay, I will discuss more about the meaning of this expression. What is the physical meaning of this expression? What is the consequence of this equation? I will discuss later in the next video, that is for the next week. So in today's class our main aim was to derive an expression for energy of the particle trapped in the one-dimensional box, and this is the expression. The Another information that we obtain when we solve the Schrodinger wave equation is the wave function. Remember, I told you at the beginning, when we solve a Schrodinger wave equation, we get two things. One is the energy, other is the wave function. We have already obtained what is the energy. Now let us find out what is the wave function. For that, let us rewrite again, okay, the equation number 6, that is the wave function of the particle trapped in the one-dimensional box is psi of x is equal to a into sine alpha x. Remember, the value of constant a is not yet found out. Okay, so still we have to find out. So this is nothing but equation 6. Now this equation 6 can be written as a into sine. We have already found out what is alpha. From the second boundary condition, we came to know that alpha should be equal to n pi by a. So instead of alpha, I will write it as n pi by a into x. Okay, this is equation 9. So this is now the solution for the Schrodinger wave equation for particle in a one-dimensional box. The wave function is given by equation 9. But the expression is not yet complete because we still don't know what is the value of a. So how to find out the value of a? We have exhausted both the boundary condition. ಯಾಕಂದ್ರೆ ಈ ಪರ್ಟಿಕ್ಯುಲರ್ ಸಿಸ್ಟಮಿಗೆ ಎರಡೇ ಬೌಂಡ್ರಿ ಕಂಡೀಷನ್ ಇದ್ದು, ಒಂದು x is equal to 0 and the other is x is equal to a. ಫಸ್ಟ್ ಬೌಂಡ್ರಿ ಕಂಡೀಷನ್ x is equal to 0 ದಿಂದ b ವ್ಯಾಲ್ಯೂ ಫೈಂಡ್ ಔಟ್ ಮಾಡಿದ್ದೇವೆ, b is equal to 0 ಅಂತ ಫೈಂಡ್ ಔಟ್ ಮಾಡಿದ್ದೇವೆ. ಸೆಕೆಂಡ್ ಬೌಂಡ್ರಿ ಕಂಡೀಷನ್ ಇಂದ ಆಲ್ಫಾ ವ್ಯಾಲ್ಯೂ ಫೈಂಡ್ ಔಟ್ ಮಾಡಿದ್ದೇವೆ, ಆಲ್ಫಾ is equal to n pi by a. ಸೊ ಎರಡು ಬೌಂಡ್ರಿ ಕಂಡೀಷನ್ ಮುಗ್ದಿದೆ. Now how to find out the value of a? For that we have one more condition, that the wave function should be a normalized function. A well-behaved function should be finite, continuous, single valued, and it should be a normalized function. So if we apply this normalization condition to equation 9, it is possible to find out the value of a. What do you mean by normalization condition? Okay, the total probability of finding the particle in the entire space should be equal to 0. That condition is called as normalization condition. So how do you write the normalization condition mathematically? I will write now. Since psi of x is a well behaved function, it should be a normalized function. It should be a normalized function. So let us apply the normalization condition. Normalization condition. Okay, in the last class, in the last video, we discussed the normalization condition both in one dimension as well as three dimensions. Since it is a one-dimensional problem, we apply the one-dimensional normalization condition. It is the total probability of finding the particle in the entire space is 1. So integration minus infinity to plus infinity, that is the entire space, entire region along x-axis, into psi square into dx is equal to 1. The total probability it should be equal to 1. But here this upper limit and lower limit we can make modification, because we already know that. Okay, so this is the picture of the particle in a one-dimensional box with x is equal to 0 and x is equal to a. So we already know that the particle cannot be present outside this box. That is, for all values of x greater than a, the probability of finding the particle is 0. Similarly, for all values of x less than 0, the probability of finding the particle is 0. So the particle will always be present between x is equal to 0 and x is equal to a. And the total probability of finding the particle within this region should be equal to 1. So we can modify this upper limit and lower limit for this particular problem as integration 0 to a. The lower limit is x is equal to 0 up to the upper limit is x is equal to a. Psi of x square into dx is equal to 1. This is the modified normalization condition, that is 0 to a, integration 0 to a. Psi of x, let us use equation 9, is square, so it becomes a square into sine square of n pi by a into x into dx is equal to 1. Okay, I have taken just the square of this because ಇಲ್ಲಿ psi square ಇರುವುದರಿಂದ square ತೆಗೆದಿದ್ದೇನೆ. It is a square into sin square n pi by a into x. Since a is a constant, we can remove it from the integration symbol and write it as therefore a square into integration 0 to a sin square of n pi by a into x into dx is equal to 1. Okay, I have just taken a square outside the bracket. Okay, so you can solve this integration. It is a very simple integration because sin square theta is nothing but 1 minus cos 2 theta divided by 2. So using that condition, you can simplify this integration here. Okay, we will avoid those mathematical part and directly show that the value of a on solving this integration finally is a square into a divided by 2 is equal to 1. A square into a divided by 2 is equal to 1. Here a by 2 is obtained after solving this integration. So we can find out therefore a square is equal to 2 divided by a, which implies a is equal to square root of 2 by a. We will only take the positive value. A is equal to square root of 2 by a. So the value of the constant capital A is square root of 2 by small a, where small a represents the length of the box. So equation 6 therefore can be written as, therefore the wave function psi of x is a into sine of n pi by a into x. So this is the wave function. Now we have found out the value of a, so we can write therefore the wave function psi of x is equal to square root of 2 by a into sine of n pi by a into x. So this is the expression I don't remember the number, maybe equation number 10. Okay, if I have made a mistake in numbering, you please correct it. So equation number 10 is nothing but the expression for the wave function of a particle of mass m trapped in a one-dimensional box of length a. So what is the expression? Psi of x is equal to square root of 2 by a into sine n pi by a into x, where a is the length of the box, x represents the position of the particle within the box, and n represents an integer whose lowest possible value is 1. N cannot be equal to 0. And in the previous slide we obtained an expression for energy corresponding to this wave function, that is n square h square divided by 8 pi square m. So these two expressions are very important. This expression is the expression for the energy of the particle. This is the expression for the wave function of the particle trapped in a one-dimensional box of length a. Okay, so in today's class our aim was to only derive this equation. When we solve a Schrodinger wave equation, we obtain energy as well as wave function, and we have obtained it. In the next class we will try to understand what is the physical significance of these two equations. So there are some very important points that we have to understand by using this equation. ಅದನ್ನು ನಾವು ಅರ್ಥ ಮಾಡಿಕೊಂಡ್ರೆ ಕ್ವಾಂಟಮ್ ಕೆಮಿಸ್ಟ್ರಿದು ಎಸೆನ್ಸ್ ಏನಿದೆ, ಇಂಪಾರ್ಟೆಂಟ್ ಐಡಿಯಾ ಏನಿದೆ ಕ್ವಾಂಟಮ್ ಕೆಮಿಸ್ಟ್ರಿದು, ಅದನ್ನು ನಾವು ಅರ್ಥ ಮಾಡ್ಕೊಳ್ಬೋದು. ಸೊ ಇನ್ ದಿ ನೆಕ್ಸ್ಟ್ ಕ್ಲಾಸ್ ದಿ ಫಸ್ಟ್ ವಿಡಿಯೋ ಲೆಕ್ಚರ್ ವಿಲ್ ಬಿ ಡೆಡಿಕೇಟೆಡ್ to understand the physical meaning of these two equations. So today we will restrict ourselves to derivation. In the next class we will try to understand the meaning of these two equations.